Hi, my name is Ella, and this is single crystal X-ray diffraction. First, recrystallization. Crude crystals are dissolved in acetonitrile, which is run through a pipette filter, which you see on the screen. This solution is then surrounded by diethyl ether in a larger vial, capped and left to recrystallize overnight. The diethyl ether will evaporate into the acetonitrile to create a supernatant and X-ray quality crystals. After the recrystallization is complete, I pipette off the supernatant to keep for later and take out my crystals and put them on a microscope slide. Now, the crystal that you choose to run is important. You want to choose a single crystal that is well formed. And here are some examples of that. Now I am going to turn on our chiller and our Rigaku desktop diffractometer. And now I am throwing away my gloves. Why? Because my PI told me to. He does not like having any extra material in the way of the instrumentation and mounting crystals because it is a little bit cramped in these desktop instruments. Here you can see that the instrument is not at a good angle for crystal mounting, so I'm going to start and initiate CrysAlisPro so that the angle omega resets itself, and I'm able to grab the pin used to mount crystals and run experiments. Here I am starting a new experiment so that I can do that. Now I am reaching in and grabbing our goniometer with a very thin piece of glass on the tip, which I am putting some stopcock grease on because we cannot run our experiments at freezing temperatures, so I have to use a thicker binding agent to make sure that my crystals actually stay at the tip of this very, very small glass pin. Now I am putting the crystal onto the pin with a very small and very careful scooping motion looking through the microscope. You saw my hand barely moved while I was putting this crystal on there. Now I am snapping that goniometer back into place and locking the machine before I open up the camera for positioning and screening. Now, as you can see, this crystal is off-center, so I'm going to rotate it clockwise to move the crystal up or counterclockwise to move the crystal down. And I have this little screwdriver-looking thing to move it left or right. This is centering the crystal in the middle of the machine, which you can see here, and this ensures good quality results and that there aren't any avoidable errors. So as you can see, as I shift through the different camera angles, it isn't centered. So I adjust again to fit inside of the center of the bullseye before going to another camera angle to make sure that it's still centered properly. It is, and we are looking good. So now I am going to move through the rest of the camera angles before I click exit and screen. Screening will take 2 frames worth of data to see if the crystal is worth your time. Here you can see that there is very little diffraction, so I'm going to say no, this crystal probably isn't worth my time and mount a new crystal. As you can see, this one's a little bit bigger. I have it centered and I'm going to screen it. Here you see a lot more of these little glowing dots. This is a very good sign. They're well spaced and they're diffracting moderately well. So I'm going to keep this crystal off to the side where I can get it again, but I still want to look and see if I can find a better crystal. Here is one that I split in half. I had a lot of really well-formed but long crystals, so I used a clean razor blade to cut it in half. It didn't work, so I'm trying one more crystal before going back to the other one. And this one is well diffracting. So I am going to move forward with this crystal. Looking at these frames, how do I know that it's good data? Well, I see a lot of bright dots that are well spaced, and these dots go all the way out to the 0.77 line, which is the resolution that I am running my experiments at and refining my data with. So I'm going to go ahead and start a pre-experiment, which will get a few more frames and calculate a strategy to run the long experiment with. Here you can see this experiment strategy as a result of the pre-experiment. And what you're going to want to do is set your exposure time, which I've done. And also, I like to collect redundant data because my machinery likes to shut down pretty frequently, so if I have the time and I'm running a crystal overnight, I don't care that it might take longer and I will run it with redundant data. After you have changed the settings to your liking, you will want to calculate a new strategy to keep those settings. And after doing that, you will see your expected experiment time and you can hit Start Experiment. So now this is going to run for quite a while, and it'll show you a little movie of your crystal moving around inside of the machine. Now my experiment is complete, and I am scrolling through a few frames to show you that there is consistently good diffraction patterns. This tells me I'll most likely have good results, and you know for sure by looking at the data reduction. In the data reduction, you can see the rint value. Your rint will appear as a percentage in Olex2, and you want it to be less than 4%. Clicking on the HKL file will open Olex2, which you will need to have downloaded on your computer. Here I can see that I have the data currently resolved to 0.65. So I'm going to go into the data reduction and finalization, and I'm going to manually change the resolution to 0.77. 0.65 is ideal, but putting it at 0.77 will improve the overall data quality, which will make my data going from completely trash to publishable. So now I'm going to open up Olex2 again, and as you can see, my rint is below 4, and my I/sigma is okay, but since that is an older version of Olex, I open it up on my laptop, and we can see that all of the data looks great. Now here I'm going to show you the importance of the shell programs. Whenever you use the Olex2 solve, you are going to have a much harder time getting a crystal structure because it only gives you these things called Q peaks, and you have to individually assign each atom. However, whenever you use the shell programs, it'll assign a lot of those atoms for you. However, they tend to be incorrect a lot of the time, so you do have to double check their atom assignments. But it makes it a lot easier if you have the ShellXL and ShellXT programs downloaded on your device whenever you are refining a structure. Here you can see my nickel terpy complex, and I have already solved it using the ShellXT program. And now I am bumping up the number of refinement cycles so that whenever I use the ShellXL program for refining, it will move a lot faster with 10 cycles instead of, say, 4 like the default. Now, after I've refined it again, you can see that the Q peaks are back and the data has changed. So I'm going to want to refine it until the shift is 0 or 0.001. Now that the shift is not changing, I am showing you that if you type the command grow into the command line, you can see if there is symmetry in your molecule. Here I do have symmetry, so whenever I type grow and fuse, the complex will grow to show the entire thing, and then fuse to go back to its half size, or only one part of the symmetric. Now I am making the molecule anisotropic, which means that the spheres are now ellipsoids, and you want the ellipsoids to look like what is on the screen, and you don't want them to look long or cigar shaped. That means that there's something wrong with your refinement. I also went ahead and added the hydrogens, which you could see aligned perfectly with the Q peaks. At this point, I am seeing a warning that says that one of my oxygen atoms can be split. But it has a weird name because Olex likes to name atoms really weird. So I'm going to go ahead and use the naming tool to name each of the atoms in my complex and turn it from something completely random to something sensible. Now that I am done naming each of my atoms, I can click on Toolbox Work in the GUI interface, and when I move here, I can select the atom names label to check and make sure that I actually did name everything correctly and that I didn't miss any atoms. And then I can go ahead and click Hide to make sure that they all go away and don't interfere with my viewing of each of the atoms. Now I'm going to double check and see which atom needs to be split, and I'm going to go to the Disorder tool. There I am going to click on the Split tool, select the atom I want split, and then escape out of that menu. As you can see, I now have 2 oxygen atoms where there used to be 1. This is called disorder modeling, and now I'm going to delete these bonds that obviously shouldn't be there between this hydrogen and oxygen. So I'm getting rid of this bond, and I'm double checking this one to make sure that it's not an actual bond and it's just showing that these are close. And now I am checking to make sure that each atom is in the right part. Whenever you are disorder modeling, you want the original atom to be in part 1 and the new atom to be in part 2. And it's important to keep in mind that every other atom, except for the ones you have split, are going to be in part 0. One of the most important parts about disorder modeling is the chemical occupancy. You want the chemical occupancies of both of your new atoms, your split atoms, to equal 1. So I have made the original atom chemical occupancy 3/4 and the new atom's chemical occupancy 1/4. As you can see, this has put our 2 split atoms right next to each other, and the molecule isn't blowing up. If I hadn't changed the occupancy, the split atom O1A would have ended up bonded to another random atom in the molecule, which we obviously don't want. So now I am going through the refinement cycles and making these new atoms anisotropic. And I am checking the XT constraint because Olex is giving me a warning that I'm going to want one of these constraints, and that removes the warning. And now my refinement is pretty much finished. So you still see a warning telling me that one atom could be split, and this is my new oxygen that had already been split, so I'm double checking it, and I'm thinking this probably isn't a good idea to go ahead and split again, but that's something I'll ask my supervisor about because disorder modeling is still something that I'm learning. Now I am going back into the toolbox at the drop-down menu that says No Acta, and I am now selecting Acta. And what this does is it generates a CIF file for my complex. Now the CIF file is what actually gives you all of the information about bond angles, bond lengths, distances, chemical formulas, and most importantly, it is what is used for publications. So I am checking over the CIF and INS file to make sure everything looks correct, and I am also updating the chemical formula to reflect what is actually modeled in my complex. So now that I've done all of that, I'm going to go into the report and make sure that I am editing the CIF as well as the INS and changing that chemical formula to make sure that everything is correct before I put this CIF through the program Check CIF. I've now moved on over to the internet where I've looked up Check CIF, and I am choosing my CIF file that I generated from Olex2 to upload and double check to make sure that there are no massive issues with my refinement. So I am sending my CIF for checking and waiting for the results. As I scroll down, I see the only major warnings that we have gotten involve basic data entry, so entering an author, giving a description of the crystal, just stuff like that. It has nothing to do with my refinement itself. And scrolling through the alert level C's as well, it looks like to be a lot of the same things. So because all of the error messages that I'm getting from CheckSif are mostly documentation based, that means that I am ready to send this file right on over to my supervisor, including the res file, the HKL file, the CIF file, and the INS file. These are all of the important files that are generated from single crystal XRD, and my structure should now be ready for publishing. Thank you all so much for watching, and I hope you learned something today. If you have any questions, feel free to leave a comment down below or reach out on Instagram. I love interacting with y'all and answering any questions you have, and I hope this has been helpful for you. Have a great day, and happy studying!